Hi everyone, I can't be there with you on this Friday, but I hope to make this video concise and very summarized very well so that you don't have to dwell too much on it. It may be long simply because I want to get through as many of these examples as possible, but know that all of these examples is based off of one, I guess, formula for the dot product, and that is specifically work. Okay, so we've talked about the dot product a little bit, and we're going to focus on the application of. But as a reminder, please note that although there is a long weekend and we're going to continue on to 7.3 on Tuesday, we still have our mini test on the Wednesday. Notice that there are no projections. In other words, there is nothing from Tuesday that's going to be on the mini test. So today's lesson counts. In other words, calculation of work counts. All right. So without further ado, let's get through this. We'll try to make it quick. I want to appeal to your, I guess, I'm not going to say common sense because there's nothing really common about this sense, but I want to appeal to just sort of logical progression. Okay, so there's a lot of different applications that dot product can do, but ultimately, all of these applications is going to give you a scalar value, a magnitude, which you know because we talked about it yesterday. If you look at the formula for this thing called work, in other words, a dot product of two vectors, it is a magnitude times a ratio. There is no direction involved. Okay? So, one of the applications is work. Work is the product of magnitudes going in the same direction. So you could see this vector and that vector is not going in the same direction. So how do we get about it? We will take a look at the dot product. The first vector, we will see how well it applies in the direction of the second vector. So this vector F, or this force, we will see the horizontal component, or rather, the component that aligns with the second vector. We will take those two magnitudes and essentially multiply it. That's what we're doing. So this function, I am doing the component of the first vector that is in the same direction as the second vector, and we're going to multiply the magnitudes. That's the dot product. How does that relate to our application? A work is you can just what is it? You can define it as some kind of force or mutons applied to a specific direction. It is considered good work and not wasteful work. I know that sounds really, really weird, but let me try to explain by working through this idea. Okay, so let's pretend that my goal is to move this box from one point to another, and I pull it by a string. When I pull it by a string, which one of the two components helps me accomplish my task, and which one of my two components is completely wasted? I hope your answer is, well, since my task is to move it from one spot to another, the amount of work that is applied in the horizontal, so Fx, helps me accomplish my goal, and the component that lifts it above and fights gravity is completely useless to my goal. And so when I say how much work is done, I'm specifically talking about how much useful, right? How much of this is actually useful in doing this work. Okay, so little thing here. If the force applied is not the same direction as the displacement, only the component in the same direction is multiplied. So what am I trying to say? Well, I'm trying to say that, take a look, because we know if this is the angle between my force and the direction I'm moving, or the displacement of the box, the adjacent over hypotenuse is cosine, and that is f of x over f. Okay, so if I am interested in the horizontal component, then that is equal to the first vector, magnitude, multiplied by the cosine. And so, since I am only interested in the useful amount of force, or the useful amount of work, I would take all of the x component and multiply it with the magnitude of the displacement. And that's where this and the d comes from. And so there is my formula. Okay, so once again, by definition, work is the dot product of the force and displacement vectors. Some details of work include the force acting on the object, the displacement movement of the object, the angle between the two functions, and when we type in and when we calculate work, Newton meters, that instead of saying Newton meters, we say it's joules. The work is done and the unit is joules. Okay, once again, work is a scalar quantity. It's not just magnitude. In other words, work can be done, can be a negative quantity. Okay, so you can think about when that actually occurs, but let's go through the examples first. Okay, simple. Box is pulled in a horizontal distance of 100 meters. Oh my goodness. Jeez. That's why. Okay. Here's the box. And I have a box. And this is not how I want it. There it is. It is pulled by a force of 500 newtons at an angle of 30 horizontal. Okay, so that's 30 to the horizontal. It is 500 newtons, and I know it is pulled a horizontal distance of 100 meters. So that's my displacement. Okay, so my displacement vector is 100 meters. I'm going to say just to the right or east. I don't know. Let's just say right. And the angle, the force itself is 500 newtons. East, 60 degrees. Sorry, north, 30 degrees above horizontal. Okay. What is the amount of work done? That immediately says how much of this force is useful, how much of this force was done to accomplish what I desired. And so, since I want the horizontal component of it, I will apply my formula, saying this is the magnitude of the force multiplied by the cosine of the angle that it makes with the displacement. That would be 500 times cosine of 30. That gets me 500 times cosine of 30, approximately 433 newtons. Okay, so that means the work done would be 433 newtons multiplied by the displacement of 100. Remember, it's magnitude. And so we have 43300 joules of work. That's it. Let's make things a little bit more complicated. The next question is going to be a ramp of sorts. A toboggan is pulled by a tension force of 40 newtons acting at 24 degrees to the ground. Okay, if the amount of work done to the toboggan is 3,654, what is a horizontal displacement of the toboggan as a result of this force? Okay, let's do it. Okay. I am pulling this way. This is 24 degrees. This is 40 newtons. And the total work is 3,654 joules. Okay, so they basically give me the answer. What is the horizontal displacement? Okay, so once again, because I know work is the force dot product with the displacement, it is also considered the f cosine theta, so the x component, or the component that is in the same direction as displacement, multiplied by the magnitude of the displacement. We have 3654 equals 40 newtons multiplied by the cosine of 24. That is multiplied by my mystery displacement. If I were to isolate the magnitude of the displacement, that is 3654 divided by 40 divided by cosine 24, it would be approximately, this is very intentional, 100 meters. That's it. So you might be asking, what do you mean by a ramp? Well, I wanted to use this example to say it won't matter what the situation is. What if this was a ramp and I was pulling like this? This is 24 degrees to the horizontal, or sorry, 24 degrees to the hill. And you think, oh, does that change anything? In fact, it doesn't. What's my displacement? My displacement is parallel to that hill. So what is the force applied? 24 degrees north of the direction vector, or my displacement. So nothing changes in the calculation. Okay, so it's still an angle of 24 degrees between the vectors, and the way you go. Yeah. I will ask the substitute to pause the video in case anyone needs to, but again, I'm trying to speak, I guess, allude to appeal to reason. Appeal to reason. That's the word I was looking for. Okay, example 3, let's do it quick. Example 4, let's do it quick. Example 5. The challenge question, I will ask the substitute to pause and I'll give you further instructions later. Okay, find the amount of work done by a 5 Newton force moving an object from here to here. So now we have algebraic vectors involved. Okay, so I'm going to draw it out just so you can visualize. Negative 2, 1 is somewhere here, and 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8 very roughly is somewhere there. I am moving an object from here to here, and that is my algebraic vector. The force applied is 30 degrees to AB. Okay, so this is my displacement vector, obviously. I am applying a pressure, a force of 5 newtons. That is 30 degrees to AB. So this is my picture. Assume the displacement is in meters and I need to find work. Okay, so work is the force vector dot the displacement vector. I know the force is not completely useful. There is a vertical and a horizontal component. I only want the horizontal component, or rather the component that is parallel to the direction or displacement. So that would be cosine 30 degrees times the displacement vector. Okay, so let's take a look at what we actually have. The force is 5 newtons. Cosine 30 is cosine 30. I need the magnitude of the displacement vector. You don't have that right now. But if you think back to 7.1, where we learned about algebraic vectors, we can find what this actual vector is. And if we know what this vector is, I can pretend this is a 90-degree triangle and find the hypotenuse of this 90-degree triangle. So let's do it. AB is, let's see, 7 minus negative 2. That's my x coordinate. And 8 minus a 1. That's my y. The vector itself is 9, 7. That means the magnitude of AB is going to be the square root of 9 squared plus 7 squared. It is going to be 130 square root. So this would be 130 square root. My final answer, let me take a look at my calculator, is approximately 50 joules. There you go. That brings us to about halfway. I'll ask the substitute to pause the video if necessary, but I will move on. Sometimes, when you have dot product, it's very useful to know how to do dot product, using the, I guess, the other formula, okay? And not just this, but rather, you know that if I do give you the vectors in terms of coordinates, you can say that the dot product of the two vectors is equal to the product of the x coordinates plus the product of the y coordinates, right? So we could do it this way. We could also do it this way. Whatever information is given, you're going to have to choose the most efficient one. For example, and we'll get back to this, okay? Determine the angle between each of the following pairs of vectors. How will we get the angle? You know that scalar. If you use this, that would be great. So let's say we try that. Okay, so we have a dot b is equal to the magnitude of a and the magnitude of b and cosine theta. The question wants this, so I know I shouldn't have this. This isn't given to me. Magnitude of a, yes, I can find it because they gave me the coordinate or the components, the ordered pair or whatever you want to call it of the vector. Vector b, the magnitude, I can also find. So these are given. So this I need to find. These two are given. So I need some kind of answer. The only way you can do this is if you apply the other definition of a dot product, right? So a dot b is equal to 4 times -3 plus 2 times 4. So the dot product of a and b is -4. -4, therefore, is equal to the magnitude of a, 16 plus 4, square root of 20. The magnitude of b, 9, 16, 5, cosine theta. The rest is history. Isolate cosine theta by dividing all of the left and all of the sides by 5 root 20. That means the angle is going to be the inverse cosine of -4, 5 over 20. Plug that into the calculator. You should get approximately, let's see, inverse cosine of -4 divided by 5. That's approximately 100 degrees. Okay, there you go. Wait a minute. You may have seen, again, if you haven't had too much practice or you have been neglecting a little bit, or you haven't been paying too much attention, you've noticed that the dot product here is a negative. What does that mean? Food for thought. The only way a dot product would be negative is if we're doing what? Negative work. If this is a direction vector or the displacement vector, I would have an angle that is more than 90 degrees. So you can say the angle, I expect it to be more than 90 degrees, which is confirmed here. Okay, so this is also telling its own story. I'd like you to try B on your own, just in case you were wondering. I put a little note here. The final answer is approximately 148 degrees. Okay. So here's a fun one. Given, so we're going to example 5 now. So pause if you need, but that example 5, here we go. Given A and B, Determine the angles between vector AB and the positive y. Let me try to visualize that for you, and so that you know what we're talking about. Given 3, 1 as A, and negative 4, 6, somewhere here, AB is this vector. Determine the angle between vector AB and the positive y-axis. So I want to find that angle. I'll give you a minute. How would you go about finding this? Okay, the substitute can pause this video if you like and really just give the students about 30 seconds to think about it. I'm going to move on. Firstly, I need to know what vector this is. Okay, algebraically. Because I know what vector a perfectly vertical one is. It could be 0, 1. It could be 0, 2. It could be 0, 1 million. As long as the x is 0, I have myself a perfect vertical vector. Okay? In other words, I'm going to use the easiest one, this one. And instead of calling it any special thing, I'm actually going to call it the unit vector in the y-axis direction. Okay? Now, if I have this vector and I have this vector, how do I find the angle? The only way we know how. The only formula that takes vectors and introduces an angle between as a formula is dot product. So anytime questions ask you for angle between vectors, immediately think dot product. Okay, so here we go. What is vector AB? What is this thing that I'm looking for? Well, let's apply our algebraic skills and pretend this is a 90-degree triangle. The vector we're dealing with is the difference of x values and the difference of y values. We got ourselves a vector -7, 5. Nice. The other vector I am dealing with is the positive y-axis vector, which is going to be 0, 1 by definition. So what is AB dot J? Well, wouldn't that be the magnitude of AB, the magnitude of unit vector, cosine theta? And we need to find that. Okay, well, the magnitude of this would be 49 plus 25, 70, root 84. And the magnitude of a unit vector by default is going to be 1. And cosine theta I need to find, which means this must be given too. Just like the previous question, if you cannot solve it, look for another way to find some value. We're going to use the previous definition that we've used before, the product of the x values plus the product of the y values. -7 times 0 is a 0. 5 times 1 is a 5. 0 plus 5, the answer is 5. So cosine theta is 5 over root 84. Angle is approximately Oh, wait. Sorry, is that 74? 49, 60. Sorry, 74. Something doesn't look right. 74. 74. Calculator should be 54.5 degrees. There it is. So what new thing did we pull out? Well, work. It makes sense to do dot product when we're talking about work. And there are sometimes we have cryptic questions where we need to use the other definition of a dot product to get us more information to apply the formula. Okay. So here's what I'm going to do. I'm actually going to ask the substitute to stop the video here, and the class can get started on example 6 as a challenge. I don't expect people to see this part of the video. In fact, I'd rather you try it here in class, finish it off at home, go back and view this video at the last bit so that you can see if your answer is correct. Okay? So you can pause the video, or if there's time before the end of class, I invite the substitute to play the video and finish off with this solution. but I'll let you choose as a class, okay? Challenge. Consider the parallelogram. Again, I'm assuming that you are seeing this after you've tried it, okay? I have a parallelogram. The parallelogram has vertices 0, 0, 2, 3, 5, 3, and 3, 0. Okay, great. Find the interior angles in which the diagonal sides intersect. So I need to find theta, and I need to find, let's call it alpha. If I find these two angles, the other two are immediately defined. Sound familiar? Why don't we get this vector and this vector and work some magic? Okay. The only relationship or the only connection we have between vectors and angles right now is dot product. Right? Let's do it. The vector from 0 to 3, 0, let's call this vector A. That goes from 0 to 3, 0. So that would be 0 minus 3. No, let's do this. So let's call it 3 minus 0 and 0 minus 0. There you go. How about the vector from the left corner to the top left corner? We'll call that vector B. That would be, let's see, 2 minus a 0 and 3 minus a 0. Well, isn't that nice? That's right here and right here. Good. Of course, you could have done it a different way, but I'm not going to. What is the angle created when A and B are, I guess, intersecting? That is the same as saying A dot B is equal to magnitude of A, magnitude of B, cosine theta. Just like the previous question, let's solve A dot B using the other definition. 3 times 2 is a 6. 0 times 3 is a 0. So 3 times 6. So 3 times 6 plus 0 would be a 6. The magnitude of A would be 3. Magnitude of B is 4 plus 9 root 13. Cosine theta. Okay. So we've got cosine theta equals 6 over 3 root 13. The angle should be approximately 56.3 degrees. Great. Well, if I have theta here, because they have to add up to a 360, and not only that, this line and that line are parallel, the exterior angle here, or the supplementary angle here, is 56.3. I can find alpha by subtracting theta from 180, and that is 123.7 degrees. That's it. That's it. Okay. I'm sure there's another way you could have done if you've used other vectors. Like we could have done this vector plus this vector. Okay, but it should result in the exact same thing. Okay. What else can we talk about? I think that's it. It's a lot more simpler than you think, as long as you understand that angle between two vectors are no longer a mystery. Hope that it makes sense. Otherwise, keep at it. Suffer well, everyone. Have a great long weekend, and we will see you very soon.